Okay. Now, today is all about what are called log rules. These are rules that will always apply to logarithms to help you expand logs, help you condense logs, and help you solve for logs, which we're going to do next class. But before we get into the rules, because we missed last class, because I didn't teach you in person and you had to instead watch a video, I just want to make sure that you understand exactly what a log is, because most students look at logs and because they've never seen them before are totally, I don't want to say terrified, but you look at a log and you basically give up because it's something new and it's something you've never seen before and you think, oh my gosh, this must be so hard. No. So let me explain exactly what's happening here. If you have, say, 2 to the power of x is equal to 16, you can immediately right? If I just plugged in 2x equals 16, your calculator would say error, or it would just define x number. Like it wouldn't actually solve for x3, right? Instead, what you have to do is in your head, you ask yourself, okay, what power do you raise 2 to equal 16? And hopefully you come up with the answer of, okay, x must be 4, because 2 raised to the power of 4 is 16. Well, they we need to have a separate operation that helps us to immediately solve for x here. Instead of always writing out that big long question, what power two, or sorry, what power two raised 2 to equal 16, they wanted an operation that abbreviated that. So they created a log. This is asking the exact same question as this, oh gosh, as this exponential right here. It is immediately asking the question, oh, let's do purple. What power do you raise 2 to equal 16? And what power do you raise 2 to equal 16? Your answer, just like in the previous problem, is 4. That's all a log is. It's asking that question. What power do you raise 2 to equal 16? So for example, let's see, come on. If I had the log base 3 of the argument 9, by the way, this is the base number, and this, what is being logged, is called our argument. So if I log base 3 of 9, this is asking the question, what power do you raise 3 to equal 9? And what should you get as an answer? 2. Done. You just successfully solved the log. That's all it is. Nothing scary. It's just an operation. It's actually the inverse operation of exponential. Okay. So now knowing that, we can go ahead and learn today about log properties. Now I know there's not much room, especially on my, but if you have room over to the left, I really don't have any. Ugh. I want another column for exponents. Because despite having learned it all the way back in Algebra 2 and using it sometimes in geometry, using it in Algebra, I'm sorry, Algebra 1, you learned it, using it sometimes in Algebra 2, as well as geometry, despite all that, you guys aren't that comfortable with exponents. Exponents. So we're going to keep going over exponents because I know that you guys just aren't that comfortable with it. So first we're going to go over basic properties of exponents and logs. You guys know if I had, say, x raised to the power of 1, this is the same thing as what? Just writing x. Wonderful. What about x to the power of 0? What is this equal to? No, not actually. If you raise anything to the power of 0, what is it equal to? Mm, okay, no, it's always 1. Always. If you raise 2 to the power of 0, it equals 1. If you raise 100 to the power of 0, it equals 1. So, remember what a log is asking. What power do you raise b to equal 1? What do you think the power has to be on b to equal 1? Yes, this is 0. Good. What about the next one? What power do you raise b to equal b? So this is like this. What power do you raise b to so that the whole thing equals b? Yes, 1. 1. Good. Good, good, good. So let's do these 2 examples over here. Log base 6 of 1. So remember, this is asking what power do you raise 6 to equal 1? What power do you raise 6 to equal 1? Yes, 0. Good. And the next example, what power do you raise 4 to equal 4? Wonderful. Yes, 1. So that's just the basic properties of log. Uno. All right. So now we're going to get into a little bit more complex. And this, just a really simple concept. But it seems to like confuse you guys. So first, we're going to go over the exponent version of log. We're going to go over. If you have an exponent, I'm sorry. Um, hmm. If you have x squared times x to the power, what do you do with those exponents? See? Like at this point, you guys should, nope, no, not multiply. That's actually what you do when you have an exponent raised to another exponent. You multiply and you get, yes, you add them. So you add 2 plus 4 and you get x to the 6th power. Almost the exact same concept here. We're adding two terms inside of a log. This is equivalent to adding two separate logs with the arguments split apart. So log base b of m times n is the same thing as log base b of m plus log base b of n. This is the product property of logs. Whenever you have two terms being multiplied in a log, you can split them apart. It's called expanding them apart into two logs being added together. Also, the reverse holds true. Whenever you see two logs with the same base, by the way, ooh, we should write that down for sure. Ugh. This thing is, okay. Must have same base. So whenever you have the same base, the reverse is true as well. And if you have the same base with two logs added together, you can condense those two logs into one log by multiplying the arguments together. Let's try. We're gonna condense first. I have two logs with the same base. I can condense them. The two logs are being added together. So to add them together into a single log, all you have to do is multiply the arguments. So I have 8 times 3x, which is equal to 24x. So this is like our m. Oh, that's this is like our m. This is like our n. So we multiply the two arguments. Now let's try expanding them. Oops. Wow, really struggling. Ooh, okay. Before we expand, I forgot. We didn't have class last class. There is something called a natural logarithm, which is a log with a base e. E being, if you didn't know, Euler's number. Euler's number is just a number that is rational. I think it's 2.718. It's rational and famous, just like pi is, but it's not quite as famous as pi. The reason why Euler's number is so important is because it appears in nature a lot. Like it appears whenever you have bacteria growth. Euler's number, it's in, I think you guys use Euler's number a lot in chemistry. If you're taking chem now, you might use E a bunch. Anyway, whenever a log has a base of E, which is Euler's number, it's called a natural logarithm. Now, because this number appears so much in nature, they were lazy and didn't want to write out log base E of something, right? Apparently, that was too long for them to write. So they instead abbreviated natural log to ln. And they wanted it to look more like a log, so what they did was they flipped the n and the l. So instead of writing nl, they wrote ln. ln is just log of base E. Mathematicians, even apparently, super lazy, and they abbreviate whenever they can. Okay. So let's go ahead and we're trying to expand the ln of x squared minus x minus 2. Now this is because it's not immediately apparent what the two terms are being multiplied. How do you think we can take x squared minus x minus 2 and make it into two terms being multiplied? How can we take x squared minus x minus 2 and rewrite it as two terms being multiplied together? Yeah, factor it. Yes, unfortunately, we are going to have to factor in this event. Or fortunately, if you're factoring. So I'm just over here going to draw a little x, and I'm going to put my a times c, which is negative 2, and my b, which is negative 1. What two numbers multiply to be negative 2, but add to be negative 1? And which one's negative, Sydney? Or anyone? Yes, negative 2. So that negative 2 plus 1, negative 1. And these are my immediate factors because I don't have any a values, so I don't have to worry about dividing by a. So you have x minus 2 and x plus 1. So now I have the log of two terms being multiplied together. I can expand this into two logs by taking the arguments and creating a log for each one and adding those two. This is how you expand one log into two logs. Any questions on the product property? After we go over this sheet, we're going to do a couple more examples. So if you're still a little confused, it's okay. There'll be more examples coming up. All right, so now on to the quotient property. We just went over the product property. Now we're going to go over the quotient property. Now, before I go over the quotient property for log, let's look at the quotient property for exponents. If you have a term with an exponent divided by, let's see. Actually, I'm going to change that 4 to 5. There we go. Okay, so if you have an x to the fifth power over an x squared, what do you do to simplify this? What do you do with the exponent? Yes, when you have an exponent or an exponent, you subtract the exponent, and you always put the numerator's exponent first. So this is going to be x to the 5 minus 2. 5 minus 2 means that our answer is x2. It's a bad. There we go. Again, you still, in order to do the log version of this problem, you must always have the same base. All right. So the log version of this property is similar. If we have two arguments being divided, we can expand this into two logs by subtracting our arguments. So this log base b of m over n can expand into log base of m minus log base b of n. Also, the reverse holds true. If you have two logs of the same base being subtracted, you can condense it into one log by dividing the arguments. So here, I'm doing the condensing first. I have log base 80, I'm sorry, log of 80 minus log of 16. I'm glad they did this problem because there's another thing I wanted to go over quickly. If you have a log of a number and there is no base, what is the invisible base? Not one. Add a 0 to it. Add those together. 10. Yes, 10. Anytime there is no base on a log, there is an invisible 10. This is called the common logarithm. If you look on your calculator and you see this button right here that says log, whoops, turn on. See that button that says log? That automatically is the common logarithm. It has an invisible base of 10. All right. So yes, these do have the same base. It's the invisible base of 10. So we can condense these. Now, we have two logs being subtracted. We condense them into a single log by dividing the argument, where the first log's argument is the numerator and the second log's argument is the denominator. And 80 divided by 16 is just, and now we're going to expand. Right now we have an argument that is a quotient, a number over a number. We can expand this into two logs by subtracting those logs with the numerator as the first log minus the log of the denominator. Any questions on the quotient rule? Where did you get the word 5 in the condensed box? Ah, you just divide 80 by 16. I just went ahead and divided. Yeah. All right. So now the power property. Actually, I don't know why. I love this property. We already went over the exponent version of it. When we have a variable or anything with an exponent raised to another exponent, you multiply the exponents. When you have, now the power property really isn't similar between the exponents versus the logs. They don't tie together nicely like the quotient and product property do, but it's still pretty straightforward. Whenever you have an exponent on an argument, what you can do is you can rewrite it with the exponent as the coefficient on the log. So basically, this n moves to the front of the log. And the reverse holds true as well. Anytime you have a coefficient in front of a log, you can move that coefficient to be the exponent on the argument. So I know that that is a little bit tricky to understand in your head, but it's really quite straightforward. So let's go ahead and try it. We have 3 times ln of 9. Now, once it's condense into a extreme log with no number in front. So what we do is we take this 3 and we make it the exponent on the 9. So it becomes the ln of 9 to the power of 3. That's a bad thing. I'm not drawing the 3's well today. And 9 to the power of 3 is 729. The reason why this power property is so important is because when we go to solve logs, in order to solve a log, you need to have just the log and an argument. You can't have a number in front. So every time we go to try to solve a log and there's a number in front, we have to move it to the exponent. That's why it's so important. But that's coming up tomorrow. Well, I guess I won't see you until Wednesday. Okay. So now let's expand it. Right now we have a log and an argument. It wants us to expand this as much as we can. The only way we can expand it is by taking the exponent and making it the coefficient. And we're done. The expand isn't as useful. Like there really isn't ever a reason you do this in math. Like the condense, you have to do it to solve for a log. But the expand version of this is like why? I guess it's just to get used to this power property. Any questions on the power property? Okay, lastly, base. We actually went over this last class in the video, so I'm just really quickly going to do this. We already went over it. Anytime we change the base, so we have log base b of a, we can change base into the common log base by taking log of the arc over log of the base. Now, the only reason you would have to do this is if you had an older calculator. Older calculators, if I'm looking at this, older calculators only compute when the base is 10. Turn on. So when we press this log button, that's the only thing that older calculators can do. But if you have a newer calculator, TI 84 or above, if you press math and you go up to log base, then you can fit in anything you want. You only have to worry about changing the base to the common log when you have an older calculator. Or change the base of this, which I don't think we ever will ask you that. But anyway, quickly what this looks like. If I'm trying to change the base of log base 5 of 138, I take the log of the argument and put it over log of the base. So what my calculator? Log of 138 divided by log, and you get 3.06. 3.06. But like I said, if you have a newer calculator, you just press math and you go to log base, and then you can do 5, 138, and you get the exact same. I believe that Desmos also allows you to use logs of different bases. So same thing here, just really quickly, I'm not even going to put it in the calculator, but you would do log of 2 over log 14. Then you would get 0.26. Okay. All right. So looking at number 19, I immediately see that this is more complex than what I saw on the previous page, right? It's not just a log plus log. Both of these logs have coefficients. So how can I take this and simplify it a little bit so that I have just a log and then I can do the product? What do I need to do first here? What can you do with coefficients on logs that condenses them into just a single log and an argument? How? Mm, not quite. Right. Okay. So you guys are. Let me show you. Let me show you if I just immediately try to like condense this into one log. Right. I know I need. Don't write this. Don't write this. I know I need to multiply the arguments, but what happens? What do I do with those? What do I have to do first with the coefficients? What do I know I can do with coefficients on logs? This was the thing that we just did. Ignore this. Don't cross it out like I did. What can I do with the two? The power property. Yes. You can make the two the exponent on the 9. What can you do with the 3? Again, you can make it the exponent on the 2. So 9 squared is just 81. And 2 cubed is 8. So now, we just have a log plus a log. How can I condense this? How can you take two logs of the same base that are added together and make it into a single log of the same base? What do you do with those numbers? It's not quotient. Quotient is when you have two logs being subtracted. Right, the product property. When we have two logs being added, we can condense into one log by multiplying the arguments. And 81 times 8 is just 648. This is as condensed as this gets. It's a single log of the argument 648. Any questions there? I think maybe I'll do another one of these because it kind of threw you off. Which one do I want to do? Let's do 21. What do I have to do first in order to combine these into a? Yeah. We take the coefficients and we make them our exponents. Now this is another exponent property that I want to go over. I think I'll write it in the power property section. If you have two terms, both raised to an exponent, you can distribute the exponent to both of the terms. So we distribute the exponent of 3 onto the original first x, and we can also distribute the exponent of 3 onto the x squared. Remember, when you have an exponent raised to an exponent, you multiply. So 2 times 3 is 6. So back up to our example. If I have the natural log of PQ raised to 3, what you can actually do here is distribute the exponent onto both of these variables. Same thing on the second log. You can distribute the 4 onto the P, and you can also distribute the 4 onto the square. And we multiply here, so 2 times 4 is 8. So now we're trying to condense into a single log. You could expand here. You could, if you wanted to, expand this into the ln of p cubed plus the ln of q cubed. But we're trying to condense. How do you take these and condense into a single log? Yes, we have two logs being added together. They can be condensed by taking the arguments and multiplying them. So we have the ln of p to the power of 3 times q to the power of 3 times p to the power of 4 times q to the power of 8. Is this simplified as this can get? No. What can you do to simplify this further? Yes. On the like variables, you can add the exponents. So we have a p cubed and a p to the fourth. We have, when we combine those, 3 plus 4 gives us p to the power of 7. And we have a cubed and a q to the power of 8. When we combine those q's, 3 plus 8 gives us 11. And this is as simplified or as condensed as our problem gets. Any questions on condensing? Again, I will try to have all of these filled out so that if you have more questions, you can come back and look at solve each one. I do want to do at least one expansion. I really want to do which one do I want? Yeah, I got 29. Oh, oh yes, 29 is good. There's one more exponent property that we didn't go over that I wanted to go over. So where does it fit in? I think it fits in with quotient. Sometimes you guys are going to have an exponent in the denominator. Does anyone know how we can get an exponent out of the denominator? This one's tricky. Everyone seems to forget this. So I'll just tell you. We can rewrite 1 over x squared as x to the power of negative 2. Anytime you have a negative exponent, that actually means is that term is actually in the denominator with the positive version of the exponent. So if you had, for example, I don't know, look at this, x to the power of negative 4, this is the same thing as 1 over x to the power of. Also, there's a third one that I need to cover. I really wrote kind of big. Does anyone know how you would rewrite x to the power of 1/3? What is that the same as? This I've actually already done. What does the denominator actually mean in the exponent? Mm, no, not quite. We're running out of time, so I'll just tell you. X to the power of 1/3, the denominator exponent is actually the root. So here, this can be rewritten as the cube root of x. Another quick example, if you had x to the power of 2/5, again, the denominator is the root, so this is the 5th root of x, and the numerator in the exponent is just the exponent. So when we did radicals, I actually did go over this, but I know it's easy to forget. So back up here on our example. Come on now, deeper. I have log of the square root of a cubed times b. How or what is the first step in expanding this? How can I rewrite that square root? Close. What type of root is this? Is it a cube root? Is there, what invisible number is here telling us what root it is? Yes, it's a square root. Anytime there's just a root symbol, there's actually invisible too. It's a square root. So we can write that this is raised to the power of 1/2. And then we also learned that whenever we have two variables raised to the same power, we can just distribute that exponent into both terms. So a cubed times 1/2 would be a to the power of 3/2, and b raised to the power of 1. So all I did there was distribute the 1/2 into both. So now I can actually expand this into two separate logs because I know that I have a log of two terms being multiplied together. To separate them, I add the two separate logs with the two separate units. And then my last and final step to finish expanding this is to move the exponents to be the coefficient. Oh, God, that's a bad one. And I'm done. I can't expand it anymore.